This is Unit 3, Alloys and Phase Rule of Engineering Chemistry, CY 8151. In the first module, we learn about phase rule. This is an introductory session on phase rule. This is the content outline. In the third unit, alloys and phase rule, we have two subheadings. First is alloys and the other is phase rule. In this phase rule, we'll be covering the following topics. Gibbs phase rule, definition of various terms involved in this Gibbs phase rule, that is phase, component, degree of freedom with relevant examples. And what is a one component system? And we are going to draw phase diagram for this one component water system and apply Gibbs phase rule. Then what is reduced or condensed phase rule? How is thermal analysis carried out, and with the help of this thermal analysis and how are cooling curves drawn? What is a two component system? And one of the examples for this two component system is lead silver system. We are going to apply reduced phase rule for this lead silver system, and how is Patterson's process used for the desilverization of lead. So these are the topics that we are going to cover in this phase rule. We look into the topic one by one. First is Gibbs phase rule. In every heterogeneous system in equilibrium, the sum of the number of phases and degree of freedom is greater than the number of components by 2. This is phase rule. Okay. When two or more different phases exist in equilibrium with each other, then it is called as polyphase or heterogeneous system. Such systems can be conveniently studied with the help of a generalization known as phase rule, which was enunciated by Willard Gibbs in 1876 on the basis of certain thermodynamic principles, which was further developed by Roseboom in 1884. And with the help of this phase rule, that is, the number of degrees of freedom of the system is related to the number of components and of phases by this equation. This is phase rule. With the help of this phase rule, it has been possible to predict qualitatively with the help of a diagram, which is known as phase diagram, the effect of changing pressure, temperature and concentration on a heterogeneous system in equilibrium. And this Gibbs phase rule is valid for any system at equilibrium, provided the equilibrium between any number of phases is not influenced by electrical, magnetic, gravitational forces or by surface action, and is only influenced by pressure, temperature and concentration. So remember, while we apply Gibbs phase rule for any system, we have taken in mind certain things. This Gibbs phase rule is applicable only for heterogeneous system where the phases involved are in equilibrium, and those equilibrium are not affected by gravitational, electric, magnetic forces or by surface action, and is only influenced by pressure, temperature and concentration. So this is the statement of phase rule. Actually, this is the outcome of the derivation which was derived based on certain thermodynamic principles. F plus P equal to C plus 2. This is Gibbs phase rule. We can write it as F equal to C minus P plus 2. Okay, this is Gibbs phase rule. To get more idea about this Gibbs phase rule, we must understand the terms involved in this phase rule. That is, what is P, what is F, what is C. Actually, P represents the number of phases in equilibrium, C is the number of components present in the system, and F is the degree of freedom for the equilibrium. Okay, so we'll learn what is F, what is P and what is C one by one. Okay, so first is phase. What is phase? Phase can be defined as homogeneous, physically distinct and mechanically separable part of a heterogeneous system which is separated from other parts of the system by definite bounding surface. Okay, to get an idea of what is phase, we must know the terms homogeneous and heterogeneous. Okay, so what is meant by homogeneous system? A homogeneous system is one which is uniform throughout in all aspects, both physically as well as chemically. So what is a heterogeneous system? A heterogeneous system comprises of two or more parts, each of which is homogeneous in itself and is separated from others by definite bounding surface. Hope you get an idea. Again, I repeat what is a homogeneous system, which is uniform throughout in all aspects, both physically and chemically. Okay, an example for this is sodium chloride in water. this sodium chloride solution, just take 2 or 3 drops of sodium chloride solution. Each drop of this solution will be alike in all aspects, both physically as well as chemically. Such a solution can be considered as a homogeneous solution. So as per the definition of phase, a phase should be homogeneous, physically distinct. What is meant by physically distinct? It should be possible to distinguish it just by viewing it. Okay, that's physically distinct and mechanically separable. By some means, it should be possible to separate that homogeneous system from this heterogeneous system. Okay, so this is the definition of phase. When these conditions are satisfied, we can consider this as a phase. Okay, homogeneous, physically distinct and mechanically separable part of a system. Which system? Heterogeneous system, which is separated from remaining part of the system by definite bounding surface. Now we'll get more clarity about this phase by taking some examples. Okay, first is solid. Every solid in a system is an individual phase and each is separated from others by definite bounding surface. So, a heterogeneous mixture of solids consists of as many number of phases as the number of solid substance in the mixture. Can you understand? See, I have taken a beaker and I have added calcium oxide and calcium carbonate in it. Both are in solid form. So, calcium oxide is a homogeneous system and calcium carbonate is another homogeneous system. When these are combined means they are mixed. I mean it's mixed, okay, and taken in a beaker, it comprises a heterogeneous system. So this is a heterogeneous system consisting of two solids, calcium oxide and calcium carbonate. So in this heterogeneous system, the number of phases is 2. Since the two constituents present in this heterogeneous system are solids, so a heterogeneous mixture of solids consists of as many number of phases as the number of solid substances in the mixture. So the number of phases in this case is 2. Okay, simply we can say a heterogeneous system comprising of solid constituents consists of as many number of phases as the number of solid constituents present in it. Okay, except the case of solid solution. Okay, each solid makes up a separate phase. Solid solution being perfectly homogeneous is considered as a single phase. Okay, now second thing is liquid. A liquid layer is considered as one phase as long as it is homogeneous and irrespective of whether it contains a pure substance or a mixture. Thus, two perfectly miscible liquids form a single phase, while two perfectly immiscible liquids in contact form two different phases. We know the concept that like dissolves like. So, polar has an affinity towards another polar substance. Similarly, non-polar substance has affinity towards another non-polar substance. So, keeping this concept in mind, we can say water has an affinity towards alcohol. So, when water and alcohol are mixed, they are completely miscible and constitutes a single phase. Though there are two different constituents, since they are completely miscible, they constitute a single phase. Similarly, when two non-polar solvents are considered, for example, benzene and chloroform, they are non-polar. So, like dissolves in like. So, again, it constitutes a single phase. Now, consider two different things. Water is a polar solvent and carbon tetrachloride or chloroform. Okay, something. This is a non-polar thing. So, when these two combine, they form two different layers. They are immiscible in nature. And so, the number of phases present in this case is 2. Then, a solute which is completely dissolved in a solvent will also constitute one phase. For example, simply the same thing I am repeating. Glucose in water, when it is completely soluble, it constitutes a single phase. But when the amount of solute exceeds or when it reaches the saturation limit, the solute doesn't get dissolved in solvent and remains in undissolved form. In such a case, it's no longer homogeneous. It has two phases in it. Okay. Now, colloids. Colloidal system, actually, solution can be classified into three types. One is true solution, other is colloidal solution, and the third is suspension, depending on the particle size. When the particle size is less than 1 nanometer, we call it as true solution. When it is between 1 to 1000 nanometer, we call it as colloids, and when it is greater than 1000 nanometer, we call it as suspension. Now, this colloids, colloid itself means a dispersed phase in a dispersion medium, similar to solute in solvent. So, it is heterogeneous and it constitutes number of phases, which depends on the number of solute present or dispersed phase present in it. Okay, alloy. Coming to alloy, this is similar to this one we have already said, no, solid solution. An alloy is a solid solution. As per the definition of alloy, alloy is a solid mixture of two different elements, of which one element must be a metal. Okay, because of the intimate mixing and formation of this solid solution, alloy is a homogeneous constituent. So, number of phases present in alloy is 1. Then coming to hydrate. We know copper sulfate exists in different hydrate forms. No? Copper sulfate, pentahydrate, trihydrate, monohydrate. Okay. In such a case, each hydrate is considered as a phase. Okay. Then coming to freezing water system. What's a freezing water system? Take some amount of water, pour it in a ice tray, place it in a freezer, and after 2 hours when you watch it, you can see some formation of ice. There will be water and some vapors coming out. So this condition we call that water as freezing water system. And so we can see 3 distinct phases. What are the 3 different phases? Ice, water and water vapor. So in a freezing water system, ice, water and water vapor are the 3 phases, each of which is physically distinct and homogeneous, and there are definite boundaries between ice, water and water vapor. So the number of phases in a freezing water system is 3. Okay. Then we'll take some other examples. Okay. This example we'll see. Calcium carbonate. See the equilibrium condition. We have to write this. Okay. Calcium carbonate giving calcium oxide and carbon dioxide. See, every solid in a heterogeneous system has to be considered as a single phase. So this is one solid, this is one solid, and this is one gas. So the number of solid constituents is 2, and each is considered as a phase. So 1 plus 1 and gas is another phase. So this is the third phase. Okay. So number of phases in this decomposition of calcium carbonate is 3. Okay. I didn't mention about this gas. Okay. A gaseous mixture being thoroughly miscible in all proportions is homogeneous. This is due to intimate mixing of the molecules. So such a system constitutes only one phase. That is, for example, mixture of nitrogen and oxygen. Now, under this condition, we have to consider one thing. See, I have taken a vessel, and in that vessel, there are 2 different types of gases, A and B, N moles of A and N moles of B. Now, when the interaction between molecules of A is greater than those of B, that is, there is greater van der Waals force of attraction between molecules of A than the van der Waals force of attraction between molecules of B. That is, greater van der Waals force of attraction is experienced by molecules of A, then the ease of liquefaction will be higher for A. So, that A molecules will be getting liquefied on the walls of the container. So, in this case, we can say the number of phases is 2. One is the 2 gases in the gaseous form constitute a single phase, and that liquid constitutes a different phase. So, the number of phases will be 2. Okay. Then, consider a gas in contact with a liquid. In such a case, the number of phases is determined on the basis of solubility of gas in the liquid. In general, greater the dipolar moment of a gas, greater is the solubility. Ammonia and water HCl and water. These are easily soluble, so homogeneous.